So let's continue solving questions that you have sent from the chapter of solid state. I've got around 18 questions altogether, but today we'll solve only the problems related to density. Then in next video the other type of problem will be solved. Okay, so I'll be starting with this first one. An atom A crystallizes in BCC with density 1.2 grams per centimeter cube, whereas another atom B crystallizes in BCC with the density of this. So there are two different types of elements. Let's say element A, which has atoms of A, and element B, which has got atoms of B, and they've got different densities. First one is little less denser, second one is quite dense. What else is given? That both forms BCC. Remember that. That means in body centered cubic unit cell they have got two atoms. That you must be knowing if you have gone through those videos which I had posted earlier. If B is 7 by 2 times heavier than A, that means the mass of B atom will be 7 by 2 times heavier than that of A. So individually masses of A and B atoms are not given. That means the atomic masses are not given. What is the relationship between the radii of A and B? So we've got to get a ratio of radius of A to radius of B. So I've already solved the problem here. I've got the solution here. You can see this. So I'm taking the first case, case 1, which has got atoms of A. Density is given. It's given in CGS unit, grams per centimeter cube. So because we're dealing with BCC, so the density of BCC is given by this, atomic mass divided by N. That's Avogadro's number, gives the mass of one atom. And you know that there are two atoms in BCC, so total mass of both the atoms present in BCC unit cell will be 2 times A by N and divided by the volume, mass divided by the volume A cube. A is the edge length of the BCC unit cell formed by this element A. So the edge length here is A with a subscript capital A, which stands for edge length of the BCC of A. So this is the density, and the other side density is already given, so we have got this equation. From this equation what we can do is we can simply cross multiply A cube other side and try to find the edge length. You know why we are trying to find edge length? Because rest of the things are given, mostly things are given. Like for example, we can compare the masses of atomic masses of A and B, because B is 7 by 2 times heavier than A. So if you can find the edge length of the cube, since you already have a relation between edge length of the cube and the radius of atom, that makes that BCC cube. So by finding this A, that is the edge length of BCC, you can find the radius of A and similarly radius of B, and we can have a ratio. So when you take out the cube root of this, it goes here. Now I'm replacing the edge length of the BCC of A with the radius. So this is the relation for BCC. A is equals to 4 by root 3 A, R, that is radius of atom. So this is the radius of atom of A. So when you cross multiply other side, you get this. This is the expression we got for the radius of atoms of A. Similarly, in second case, we've got atoms of B. Density is given, so I'll find the density. This time, instead of using A, I'm using B. A is the atomic mass of A, whereas B is the atomic mass of B. So atomic mass divided by Avogadro number gives the number of mass of one atom into 2 total mass of all the atoms present in BCC divided by the volume of BCC body centered cubic unit cell, which is A cube. But this time the edge length of this BCC and edge length of this BCC won't be same. So the edge length here is marked as AB cube. Similarly, cross multiply and try to find the value of AB, which is the cube root of this. Now I'll replace this AB again with the radius. So edge length is replaced with the radius of atoms of B. Solve and get the value of radius of B. So we've got equation 2. Now we've got the radius of A in expression 1 and radius of B in expression 2. So we divide expression 1 by 2. So expression 1 has got this divided by the expression 2 this. So this whole thing topples, it goes up. This also numerator goes to numerator, and whatever is in numerator goes to denominator. They cancel. That you can easily make out. How do they cancel? So ultimately we're left with this. I can replace the mass of B as 7 by 2 mass of A, because B is 7 by 2 times heavier than A. So AA gets cancelled. So ultimately I'm left with this, which I calculated, and I got this as 1.298. So the radii ratio of A to B is 1.2. That means A is 1.2 times larger in terms of radius than B. So this is the answer. Okay. Now we'll solve another problem. The other one is, let me see which one here. I've given numbers here, number 7, because I'm picking up only those problems which are related to density. So we've got number 7 question here. An element with molar mass 2.7 into 10 to the power minus 2 kg per mole. So what is given to us is the mass of 1 mole, because it's per mole. Mass of 1 mole we usually write in grams because molecular mass taken in gram, is 1 mole, but it's given in kg. So we can easily convert this kg into gram. So we'll have mass of 1 mole of this element in grams, which is molecular mass taken in grams. That much you know from your previous knowledge of whatever you did in class 11. Forms a cubic unit cell. So it is only given that it forms a cubic lattice, but we've got 3 cubic lattice you must be knowing: simple cubic, body centered cubic, and face centered cubic. So it's not given whether it's face centered, body centered, nothing is given. It's only given that it's cubic lattice, and the edge length of that cube or unit cell is given 405 picometer. Pico is 10 to the power minus 12 meter, you understand. If the density is 2.7 into 10 to the power 3 kg per meter, so even density is given in SI unit, kg per meter cube, density of this element. What is the nature of the cubic unit cell? What is the nature of the cubic unit cell? How do you find the nature of the cubic unit cell? How do you find whether that cubic unit cell is simple cubic or body centered cubic or face centered cubic? That we can easily find out from the density data, because density is given here. From the density data, if we could find how many atoms are there, because in the formula of density there are number of atoms, So if you can find the number of atoms that is present inside the unit cell, for example, if you find the number of atoms as 1, it's simple cubic. If there are 2 atoms, then it's BCC, and if you've got 4 atoms, then it is FCC. So it is just a matter of finding how many atoms are present in the unit cell. So what is given to us is molar mass. So this is the solution. We've got molar mass. I'm sorry about these impressions. I have a drawing at the back and I use sketch pen, and because of that these impressions are coming. Doesn't matter. So molar mass is given, these many kgs per mole. I wanted it to be converted to, because we are more comfortable working with grams, like we've been doing that since class 11, that we take molecular mass in gram, that becomes 1 mole. So I wanted to convert this kg into gram. So instead of kg, there's 1000 gram per mole. So ultimately, when you get rid of all the zeros, you're left with 27. This is 27 because of the impression is coming like that. 27 grams per mole. That means every single mole, 1 mole, weighs 27 grams. That is molecular mass taken in grams. So molecular mass or atomic mass, because these are molecules this time. So if it's atom that makes crystal, then we take atomic mass. If it's molecule, we take molecular mass. So here A, that is atomic mass or molecular mass, is 27. So A was not given. Why do we need A? Because in the formula of density, you have already seen, we've got to divide atomic mass or molecular mass, whatever makes the crystal, by the Avogadro number to get the single mass of single atom or mass of single molecule. So this time it's molecular mass, 27. So how do you find density? Density is number of atoms into mass of one atom, A by N, divided by the volume, because it's a cubic unit cell. So volume is A into A into A, edge length into edge length into edge length, A cube. Now A, that is the edge length of this unit cell, is given. How much? Here, it's given 405 pm. So again, I've got to convert this unit because we are dealing with grams, CGS unit. So I want to convert this pico. Pico is 10 to the power minus 12. And meter is converted to 100 centimeters. So when you get rid of 0, so ultimately we'll have 405 into 10 power minus 10 centimeter. So now unit conversion is over. So I'll be substituting the values of density here. Density is this much. Okay, density here. Yeah, I've got to convert this into grams. So from kg, it's converted to grams. Okay, kg is 1000 gram, and meter cube is 1 meter is 100 centimeters. So 100 to the power 3, because meter to the power minus 3 goes down and becomes meter to the power 3, and 1 meter is 100 centimeter to the power 3. Z over here stands for number of atoms, which we don't know, so let it be as Z into atomic mass or molecular mass is 27. Avogadro's number is there, and this edge length is given a power 3, A cube. Then when you cross multiply, and find Z, some cancellations are required. So if you use calculator, you'll come to know that Z comes out to be 4. Now tell me, if you have 4 atoms in a cubic unit cell, the cube has to be, or the lattice has to be FCC, that is face-centered cubic unit cell. So this is how we solve this 7th problem. Now let's see the other one. The other one will be number 2 now. For this, you have to have some knowledge of sodium chloride crystal. How sodium chloride forms a crystal. In a sodium chloride crystal, chloride ions, that is anions, it forms FCC. You got to revise those previous classes, like whatever videos I posted for solid states. There are so many videos. Out of that, you revise if you're not familiar with the crystal of sodium chloride. So a crystal of sodium chloride would look like this, where these corners of face-centered cube are occupied by chloride ions, and even faces, the entire FCC is made up of chloride ions. So these blue ones are all chloride ions, and in the octahedral void, sodium ions are trapped. Now, where you find octahedral void in FCC, in the middle of every edge, you know, there are 12 edges in a cube. The center of all the edges are octahedral void. So there's one octahedral void here, here, here. So these are sodium ions. These red ones are all sodium ions. And there's one octahedral void right at the middle of the FCC here. So there is one sodium ion here at the center of the FCC, or face-centered cubic unit cell. So this is NaCl type of crystal. But problem over here is, question number 2 is not exactly dealing with sodium chloride. It is dealing with a compound called AB, which has got rock salt, which is sodium chloride type of crystalline structure. That's why I drew the crystalline structure of AB exactly like sodium chloride, where I placed B at the corners of the FCC on the face centers, exactly the way chloride ion exists in sodium chloride, and A I placed in all the octahedral voids in all the edge center and at the center of the FCC. So this is the type of crystal that AB forms. Now the formula weight means, from the formula of A and B we can add the masses of A and B. The total mass is given as 6.023 into Y. Now this Y is an arbitrary number, so Y could be anything, so let it be Y, it's just a constant. So 6.023 into Y is the mass of this. We need mass because we are dealing with the density, so this is the mass of a single unit of AB, 6.023 into Y, sorry. Now the closest AB distance is also given as Y to the power 1/3 nanometer. Now what is closest AB distance? Because I know A lies in the octahedral void right at the middle of the edge. So the closest distance of AB is this. And this is the entire edge length, you know. So from this data, this closest distance between A and B, you can find the edge length of the cube, because edge length will be the double of closest distance. This whole length, edge length A, small a we write for that, is just the double of the closest distance. So the closest distance is Y to the power 1/3 nanometer. And the double of that, this plus this, is the edge length. So this can be used for finding edge length. Now what are we finding? We'll be finding the density. Okay, so we need density, that's why this mass is given. Now over here, most of the things are given till the end in SI unit. So I want to continue in SI unit. So instead of converting to CGS, I'll stick to SI unit. I'll calculate density in terms of SI unit only. Okay, so, and by the way, this is not NCERT question, it is IIT 2004 question. So since I am supposed to find density of the lattice, so first thing I need in density is the mass of AB, because mass by Avogadro's number is required. So how do you find mass? Mass we can calculate like this, because mass is given as 6.023 into Y, but that is in AMU. If you take that in grams, that will be taken as molecular mass taken in gram. Okay, but we won't be taking in grams, so from gram I need to convert to kg. So I divided that gram by 1000, that is 10 to the power minus 3, to convert it into kg. So this is now these many kgs per mole. So this is the molecular mass I can take in kg. Then the edge length, this whole length, is 2 times the closest distance between A and B. So 2 times closest distance is Y to the power 1/3 nanometer. And I'll replace the nano also with 10 to the power minus 9, because I'll be dealing with SI unit. In SI unit, nanometer is not a unit of length, it is meter. So I've replaced that nano with 10 to the power minus 9. So after this, so density now will be 4. Why 4? Because in FCC there are 4 units, you know, 4. If atoms are there, 4 atoms are there. If molecules are there, 4 molecules are there. So 4 times, this is A by N, that's atomic mass or molecular mass, divided by Avogadro's number, which gives the mass of one atom or mass of one molecule. So mass of one atom or molecule into 4 gives the total mass of all the atoms present in FCC, divided by A cube, that is the volume of the FCC cube. Now A over here, since you have already seen, mass is 6.023 into Y into 10 to the power minus 3 to convert it into kg, so that's the mass, divided by Avogadro's number. Then A is, that is the edge length, is 2 times the closest distance, that is Y to the power 1/3 into 10 to the power minus 9 cube. Then 2 to the power 3 is 8, there is 4, these are getting cancelled. Y is also getting cancelled because Y to the power 1/3 cube becomes Y and Y cancels. So after everything, you know, I got 1/2, and which is 0.5 into 10 So I got 5 kg per meter cube. Remember this time density is in SI units, so kg per meter cube. So I got the density. So what was asked? I was asked to calculate density. But it's also given that the density of the lattice is already somehow found, by some experiments maybe. So experimentally when they calculated the density was not matching with what we have. What we calculated just now is 5 kg per meter cube. That's with the standard data. But the observation is 20 kg per meter cube. That means there is an abnormal increase in the density of the crystal. Normally it's supposed to be 5 kg per meter cube according to the way it forms FCC, but actual observation is 20. So there is an increase in the density. That means this crystal is defective. That's why we are asked to calculate or just predict the type of defect. So I've written here that since there is an enormous rise in the density, so this is all because of some impurities. Whenever a crystalline structure is made impure, when something's added to it, naturally its density will rise. And those, so here what has happened is, it is because of the metal excess defect. There are some impurity defects that I had discussed. In fact, I've separately posted another video on YouTube regarding the type of defects that ionic crystal experiences, and there is a part of doping also there. So there you'll find that in metal excess defect, where there will be excess of metals accumulated in a defective crystal, or sometimes if it's not metal, then the anion part, not the positive part, maybe anion is excess. If one of them is excess, whether the cation or anion, then the density will rise enormously. So this rise in density therefore indicates that there is excess of cation or anion, which is given here. So that answers the whole thing. After that we've got number 5. What is there in number 5? Remember, all these questions are not mine, you had posted these, and these are wonderful questions, are quite close to what we get in exam in HS. Number 5. Aluminium crystallizes in a cubic closed pack structure. Now, what is cubic closed pack? There are 3 types of cubic lattice or unit cells, simple cubic, body centered cubic, and face centered. And if you calculate the packing fraction, which you must have calculated or you must have gone through if you have carefully seen the videos I posted, then in the packing fraction, the most efficiently packed crystal is FCC, which is 74% packed. So because of that, the FCC, that is face centered cubic, being the most closely packed cubic lattice, is also known as CCP, that is cubic close packed. So among 3 types of cubic lattice, most close packed is FCC. Okay, so it is FCC. And the metallic radius, that is R, of the aluminum atom is given 125 pm. Now what are we supposed to find? Find the length of the side of the unit cell. That means R is given and length of the side means edge length have to be calculated. So it's a simple case of finding A from R. But for that you require the type of lattice it's given, it's FCC. So that's how I start. Radius is given in 125 pm unit. I'll convert that picometer into, pico is 10 to the power minus 12, into meter is 100 centimeter. So into centimeters, ultimately radius of aluminium is 125 into 10 to the power minus 10 centimeter. Now I'm supposed to find the edge length. There is no need of calculating density here now, at least for this case, because R is given, A is required, so we'll find this. This is the relation between A and R for FCC. This calculation was also there in that video which I posted. You are supposed to derive this actually. So A is equals to 4 by root 2R. In case of BCC, remember what was the relation? A equals to 4 by root 3R. But in case of FCC, the relation between A and R is A equals to 4 by root 2R. R is given, so I replace the value of R and I calculated A as this much. So I got the edge length. Now what are we supposed to find? How many unit cells are there in 1 centimeter cube of aluminium? So we've got a small piece of aluminium, 1 cc of aluminium, which is almost around this. And within that small piece, whose volume is 1 centimeter cube, how many unit cells are there? There are millions of unit cells, I know, because each unit cell is extremely small because it's in atomic level. So extremely small. So within 1 cc, which is quite big compared to the size of 1 unit cell, there will be numerous unit cells. So how do we find? You see, it's like finding, if you have a large box, for example, you've got a large box here. Its volume is 100 liters, and there are smaller boxes inside this whose volume is only 5 liter. Now, if it's asked how many such boxes are inside this, if this is completely filled with small boxes, how do you find? You've got a volume of the entire large box and the volume of smaller boxes which are lying inside. So how do you find? It's very simple. You just have to divide the volume of the total volume of the entire large box by the volume of the small box. That's 5 liter, and that gives you 20. That means there are 20 such smaller 5 liter boxes which completely fix 100 liter. So if you divide the total volume of aluminium, which is how much? 1 centimeter cube, by the volume of each unit cell, then you can find how many unit cells are there. And that's what I've done. You see? volume of a single FCC is cubic, so A into A into A is already calculated, so it's A cube. Okay, it's hidden here, A cube. Now, how do you find number of unit cells? Volume of volume of the total aluminium, that is 1 cc, divided with the volume of 1 unit cell. You see, gives the total number of unit cells present in that 1 cc of aluminium, which I calculated to be 2.26 into 10 power 22. So for the time being, I'll post this much. Okay.